SwayamPrabha. Digital India. Educated India.
Good afternoon, everyone. Today we will cover the last part of general methodology related to finite volume method, and specifically we are going to cover the issues that arise out of presence of second order derivatives in the governing equation. Again, you can see the domain. We have zeta equal to constant and eta equal to constant lines, and we have defined ABCD control volume, which has a center at I comma j, and the segments are AB, BC, CD and DA. We will consider Laplace's equation del square phi del x2 plus del square phi del y2 equal to 0, and if this equation is integrated over ABCD, then we can write applying Green's theorem that this is integral ABCD h dot nds equal to 0, where h dot nds is del phi del x dy minus del phi del y dx. This is following Green's theorem, and so we will integrate basically equation 20b, and then this integration can be written as we have seen that if this integral means we have to integrate along the segments AB, BC, CD and DA. So exactly we have done that. The quantities are del phi del x dy minus del phi del y dx. So del phi del x at I j minus 1, j minus half. So this is basically we are integrating over ABCD. Now the del phi del x has been defined at this point, which is basically between A and B, and coordinate of this point is I j minus half. So del phi del x at I j minus half into delta y AB, that means A and B point, their vertical distance delta y AB minus del phi del y at the same point into delta x AB. Delta x AB means horizontal distance between A and B point. So this is the first line, that means integration of del phi del x at this point into delta y minus del phi del y at this point into delta x. Next we have to go along BC segment, that means we have to define the quantities del phi del x and del phi del y here. So del phi del x at I plus this coordinate of this point is I plus half j, and so del phi del x I plus half j into again delta y, and this delta y is the vertical distance between point B and C, and then again del phi del y at this point, which is I plus of j, into the horizontal distance between point C and point B, the horizontal component. So basically we are multiplying del phi del y at this point into delta x bc. So this part is the second line. Similarly, third line will be del phi del x has to be evaluated at, this is at this point, which is basically I j plus half. I j plus del phi del x at I j plus half, del phi del y at ij plus half, and they will be multiplied by again delta y cd and delta x cd. Then at this point, that means del phi del x at I minus half j and del phi del y at I minus half j, and del phi del x will be multiplied by delta y. Delta y is basically the vertical distance between point A and D, and so delta y dA, and then delta x dA, the horizontal distance between point D and point A, delta x dA. So del phi del y at I minus half j into delta x dA. So this is the basically if we perform the integral along the segments AB, BC, CD and DA, if we can evaluate this, we are through. Our integration is over, and basically we have evaluated this integral, and that is what is our target. So we will see how we can do it step by step. So in order to first we evaluate the first line of equation 22, which is given by del phi del x at I j minus half into delta y minus del phi del y I j minus half into delta x. So at this point we have to find out the gradients del phi del x and del phi del y, and then we have to multiply that with the horizontal distance between point A and B, and del phi del y you have to find out here. Then the vertical, sorry, del phi del x you have to find out here. We'll multiply it with the vertical distance between point A and B, and then we'll find out del phi del y here and multiply with the horizontal distance between A and B. Now in order to do that, we have to find this quantity del phi del x at I j minus half and del phi del y at I j minus half. Now how we can do that is the question. So we can do that by considering the mean value of, for example, if we calculate del phi del x at this point, by calculating mean value of del phi del x over this domain. This domain is not ABCD, it is rather, if we take this point as the midpoint, then the cell which is being defined is A prime, B prime, C prime, D prime. This is a pseudo definition, rather we will not this is not being used to evaluate the Laplace's equation over the domain of interest. Domain of interest is still A, B, C, D, but since we have to find out del phi del x at this point or del phi del y at this point, what we'll do, we'll calculate mean value of del phi del x over this domain. If had this been the center of a cell, then this would have been A prime, B prime, C prime, D prime would have been the element surrounding that cell, and then we have to find out mean value of del phi del x on this area A prime, B prime, C prime, D prime, and that will be eventually defined at I j minus of. So that is what we have written, that this quantity is evaluated at the mean value over this area. This area we have defined as B prime, B, C prime, D prime, A prime, B prime. And if we calculate the mean value of del phi del x on this domain, it will be eventually, as I said, it will be defined at the point I j minus of. At the point I j minus of. So we will do that integration. So we have written del phi del x at I j minus of. This is equal to, as we said, it's a mean quantity of del phi del x on this domain A prime, B prime, C prime, D prime, which means basically area integral of del phi del x dx dy divided by the mean area of A prime, B prime, C prime, D prime. And then if again if we apply Green's theorem on this integral, we can write 1 by again area into line integral of phi dy, which is equation 23, and del phi del y at the same point I j minus of, it is calculated as double integral of del phi del y dx dy. So area integral of del phi del y on the area A prime, B prime, C prime, D prime. Here also we can see A prime, B prime, C prime, D prime divided by the area. So this is minus quantity because the first line of the integral we have seen del phi del x into delta y minus del phi del y into delta x. This quantity again line integral of phi dx divided by area. So we have first evaluated line integral of phi dy, line integral of phi dy over A prime, B prime, C prime, D prime. And now we can clearly see that phi dy we have to integrate. So phi at here it is, this point is basically I j minus 1 point. Phi I j minus 1 into delta y, that means vertical distance between A prime and B prime, then phi b into again delta y, that is vertical distance between B prime and C prime, delta y, B prime, C prime, then phi at this point, which is basically phi ij. We can see phi ij into again delta y, C prime, D prime, then phi a into delta y, D prime, A prime. So that completes the integration, and that means equation 23, this line integral is evaluated. If we divide it by the area, we are through. We'll get del phi del x at I j minus of this point. That was what of interest. Then we'll integrate again on ABCD. If we find values of del phi del x, del phi del y at these points between A and B, between B and C, and so forth. Now equation 24 is integral phi dx over again this area a prime b prime c prime d prime. So that is we can clearly see that phi here at ij minus 1 into delta x, that is horizontal distance between a prime and b prime, delta x a prime b prime, phi at b, then delta x b prime c prime, then phi ij delta x c prime d prime, and phi a into delta x d prime a prime. So then again this 24 integral phi dx we have found out. 23 integral phi dy we have found out, and we have written here this has to be divided by the area. Now we have to find out the how to define this area. Now basically this area we can again define as SAB. SAB means S A prime B prime C prime D prime. This area we'll call as SAB, and this is basically the area of a quadrilateral, and that is A prime B prime into B prime C prime. So this and mod value of that. So we have one after another found out this magnitude, and then we evaluated this. You can do it little meticulously. I'm giving you one example how the quantities have been defined, like delta y a prime b prime is the vertical distance between the point a prime b prime. This is equal to minus delta y c prime d prime. This is minus delta y c prime d prime, vertical distance between d prime and c prime, and this is equal to delta y a b. Again this is vertical distance between point a and b. So these are all same. If the grid is not distorted, these are likely to be very close to each other. And delta y b prime c prime, that is delta y vertical distance between b prime and c prime point, that is delta y j minus 1 j. Very clear, j minus 1 j. So this way delta y a prime b prime, then delta x a prime b prime, these have been such quantities have been calculated, so that finally a prime b prime is what? Delta x a prime b prime I plus delta y a prime b prime j. And what is b prime c prime? B prime c prime is delta x b prime c prime I plus delta y b prime c prime j. So this is multiplication of these two quantities, and we take a mod value of that. Now if we component wise we have found out each component. If we substitute them, final expression will be SAB equal to delta x AB into delta y j minus 1 j minus delta y AB into delta x j minus 1 j. So delta x AB into delta y j minus 1 j minus delta y AB into delta x j minus 1 j. That is the area of this quadrilateral A prime B prime C prime D prime. So if we refer to equation 23, we will be able to see we have seen how phi dy has to be integrated, how phi dx has to be integrated, and what is the final expression of the area A prime B prime C prime D prime. Having found out that, we will be able to write from equation 23 and 24, that's what we mentioned was our target, del phi del x at I j minus half we can now, whatever we have done, this is phi dy expression, and then you have to divide it by area, and if we have found out everything, so we can get this expression, which is delta y AB into phi ij minus 1 minus phi ij plus delta y I minus 1j into phi b minus phi a divided by the area. Then del phi del y at I j minus half, same point. This is minus delta x AB into phi I j minus 1 minus phi I j plus delta x j minus 1 j into phi b minus phi a divided by the area. We found out, as I said earlier, that phi dy, phi d, this is phi dy, this is phi dx, and this is the area. So we are dividing integral phi dy by area, integral phi dx by area, and we are getting 26 and 27. Now, if you recall what was first line of equation 22, which was to be evaluated, we have evaluated this quantity, we have evaluated this quantity. Now this quantity del phi del x has to be multiplied by delta y AB, that is vertical distance between point A and B, and del phi del y we have found out here, that has to be multiplied by horizontal distance between A and B, delta xab. So these two quantities we have, so long we have spent our time in finding out these two terms. Now we have to multiply these two terms with delta y and delta x. So we'll come to equation 26 and 27. So 26 now, for example, if we multiply by delta y AB, and 27 if we multiply by delta x AB, we will be able to evaluate the first line, and by doing so we can see we are getting equation 28. This is basically first line of equation 22. Now if we look at these quantities, we will see that here all these quantities, delta x square AB, delta y square AB, area AB, delta x AB, delta xj minus 1j, delta y AB, delta yj minus 1j, and again area, these are all comprising of, all these are comprising of the geometrical parameters, and here the field variable, that is the dependent variable, is here phi I j minus 1 minus phi I j and phi b minus phi. So we can say that the first term is basically MAB into phi I j minus 1 plus phi I j, where MAB is given by these geometrical parameters. I mean, phi MAB is a term comprising of geometrical parameters. Similarly, second term, phi b minus phi a, that is being multiplied by this quantity, which is again geometrical parameter. And these two geometrical parameters, we are giving a new nomenclature, MAB and NAB. So MAB into phi I j minus 1 minus phi I j, NAB into phi b minus phi a. These two, I mean additive quantities of these two is equation 28. So we have evaluated equation 28 is basically equation 28 is basically evaluation of first line of equation 28. Now we'll evaluate the second line of equation 22, which is again del phi del x at I plus half j. I plus half j means at this point, and del phi del y at j plus half j, j plus half j at this point. Del phi del x at this point will be multiplied by delta y bc, that means vertical distance between b and c, and del phi del y, having evaluated that, will be multiplied by delta x bc, that is horizontal distance between c and b. So we have to, in order to find out this del phi del x quantity and del phi del y quantity here, like we did in earlier case, we have to integrate them over this domain, which is, we can call domain of interpolation, and this we are defining as a double prime, b double prime, c double prime, and d double prime. So this domain of interpolation, on this we will find the mean value of del phi del x and mean value of del phi del y, which is meant that they are being defined at this point. So del phi del x at I plus half j is basically double integral of del phi del x dx dy divided by area of this new quadrilateral a double prime, b double prime, c double prime, d double prime. And again, if we apply Green's theorem here, this integral means 1 by area line integral of phi dy, and del phi del y at again the same point I plus half j, this is 1 by area double integral, surface integral of del phi del y dx dy, which is equal to minus 1 by area into line integral of phi dx. We did same thing for our earlier case for evaluating first line of equation 22. This is second line, and in the second line these are the terms del phi del x and del phi del y, del phi del x, del phi del y. How they are to be evaluated, we have clearly written it down. Now after having evaluated this, will be through. So del phi del x at I plus half j point is 1 by area, again we wrote a surface integral of del phi del x, which is basically line integral of phi dy. So phi dy line integral over the segments a double prime, b double prime, b double prime, c double prime, c double prime, d double prime, and d double prime, a double prime. It is just around the this contour we have to go, and that is how we have done. Phi b into delta y a double prime, b double prime, phi I plus 1j delta y b double prime, c double prime, phi c delta y c double prime, d double prime, plus phi ij into delta y d double prime, a double prime. And in order to find out del phi del y at same point, again we have to integrate phi dx over a prime, a double prime, b double prime, b double prime, c double prime, c double prime, d double prime, d double prime, a double prime. And if we do that, phi dx is phi b into delta x a double prime, b double prime, phi I plus 1j delta x b double prime, c double prime, phi c into delta x c double prime, d double prime, phi ij delta x d double prime, a double prime. So these are the integrals, and divided by Similar way, if we now can calculate the area of this quadrilateral, A double prime, B double prime, C double prime, D double prime, which we have done here. Again, we have done some parametric evaluation, delta y A double prime B double prime equal to minus delta y C double prime D double prime equal to delta y I plus 1. So this way we have calculated these parameters, and as we know that this area means basically A double prime B double prime into B double prime C double prime, and A double prime B double prime means is X component into I, Y component into J. Similarly, B double prime C double prime means it's X component I plus Y component into J. So here we can see delta X B double prime C double prime I plus delta Y A double prime B double prime J, and delta X B double prime C double prime I plus delta Y B double prime C double prime J. I have done a small mistake. This will be delta X A double prime B double prime. This, please note down this mistake. This will be delta X A double prime B double prime I plus delta Y A double prime B double prime J. So if we evaluate this and then we divide this integral values, integral phi dy and integral phi dx, we will be able to get these two quantities, del phi del x at I plus half j, del phi del y at I plus half j. Again, we have to, having done that complete evaluation of the second line of equation 22, we have to multiply this with delta y b double prime c double prime, and we have to multiply this with delta x b double prime c double prime, and then again we will get an expression. Similarly, we will evaluate the third line. Third line means del phi del x at I j plus half and del phi del y at I j plus half. So basically then we have to find out del phi del x at this point, that means I j plus half, and del phi del x at this point I j plus half here, and then again we have to do the multiplication, and for finding out here again we have to define a new area and we have to integrate those quantities on those area and finding values here. Then we have to find that by delta y cd and delta x cd. So this way, if we complete the entire integration, this point into delta x delta y component value of this point into delta x delta y component value at this point into delta x delta y value of this point into delta x delta y, then we have evaluated the entire integration. But in order to do that, all this del phi del x and del phi del y quantity are being defined here, 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 here. So for defining here, we have interpolated it on this domain, we have interpolated on this domain. Similarly here, we have not shown, we have to interpolate if we want to find out on this domain. So this way we have to find out all the quantities, and then if we assemble them, we'll see just from the first line, if you recall, we got equation 28, basically geometric parameters MAB multiplied by phi ij minus 1 minus phi ij, again NAB phi b minus phi a. So every line will generate some such geometric parameter equivalence and multiplied by the difference in field variables. Exactly, we can see A may be multiplied by phi I j minus 1 minus phi I j, N A B phi B minus phi A, MBC from second equation we'll get these two terms, MBC and NBC. It is multiplied by phi I minus 1j minus phi ij. This is multiplied by phi C minus phi B. So we will, from the third line we'll get these two terms, and from the fourth line we'll get these two terms. So equation 22 is now completely evaluated as equation 31. You can see, as I mentioned earlier, MAB, NAB, MBC, NBC, MCD, etc. are all geometric parameters. So these are basically geometrical parameters. We have written MAB, NAB, MBC, NBC, MCD, NCD, MDA, and NDA. And how they are geometrical parameters, we have understood that these are different projections of line segments on horizontal line or on vertical line. Basically, vertical distance between if we define a line segment by 2 points, vertical distance between those 2 points and horizontal distance between those 2 points, then the area of the quadrilateral and such parameters. So we these are the geometrical parameters. And equation 31, if you see, we can see that phi ij minus 1, phi ij, phi ij plus 1, phi ij, all these ij subscripted variables, these are basically nodal points, well-defined nodal points where the grid lines are intersecting. But phi C, phi B, phi A, these are not nodal points. These are between, two nodal points, lie between two nodal points. So they have to be evaluated in terms of nodal points. Like phi A. See this phi A, it is basically it is not ij or j minus 1 ij minus 1 or ij plus 1 or I plus 1 j plus 1. This is falling here, which is basically I plus half and j minus half, right? So this intersection between j minus half and I minus half. So if we want to find out this point in terms of 4 neighboring coordinates where things are well defined, it is crossing I j minus 1 line. So this point, then basically we can say ij, then this is I minus half j, and this I minus 1j, sorry, and this is I minus 1 j minus 1. So this is I minus 1 j minus 1 point, this is I j minus 1 point, this is basically ij point, this is I minus 1 j point. So we have written all these points, and the mean value of that divided by 4 is the coordinate value of phi A. So that is how phi A, phi B, phi C and phi D, they have to be evaluated. Because phi A, ABCD was defined such a way that its center point is ij, but its vertices are not falling on intersection lines of the grids I plus 1, I minus 1, j plus 1, j minus 1. So if we do that, phi A, phi B, phi C, phi D, just the way phi A has been calculated, if we follow the same calculation, phi B, phi C, phi D, and substitute in the equation that we got as equation 31, we will be able to get equation 32. So equation 32 is basically evaluation of the line integral of basically del phi del x and del phi del y along a b c d, which is the control volume. And here we can see that basically it is comprising of multiplication of geometrical parameters and the phi value at different nodes. Ij is a node of interest, I plus 1j, I minus 1j, ij plus 1, ij minus 1, I plus 1j plus 1, then I minus 1j, I minus 1, j minus 1, then I plus 1, j minus 1. So all the nodes we have to see appearing. We have to get participated in this calculation, and that is how equation 32 has been obtained. And in the equation 32, if we carefully now look at it, every phi term is having some coefficient. Every phi term is having coefficient. Now phi ij is having coefficient MAB plus MBC plus MCD plus MDA. So, and this equation is equal to 0. That means this phi ij with its coefficients, if shifted to the other side of the equation, and then we can explicitly get expression of phi ij by dividing the remaining terms by this term, MAB plus MBC plus MCD plus MD. So that is what we have done. We are calling this as phi ij star. This is all the remaining terms on the other side divided by MAB plus MBC plus MCD plus MDA. These four terms, this term basically, these four quantities, bracketed terms together is the coefficient of phi ij, and we are transferring this to the right hand side, dividing the entire remaining terms with this term, and we are getting phi ij. We are calling it phi ij star. This is explicit evaluation. And if all phi's, right hand side phi's, are at the nth level, then phi ij, left hand side phi I, is at the advanced level. If we are going from n to n plus 1, this is, we are not calling it n plus 1. You can say it is pseudo n plus 1 is this, and then this start term can be the initial evaluation. In order to accelerate the calculation, we can then call that phi ij n plus 1 equal to phi ij n plus lambda. Lambda is over relaxation is an over relaxation parameter phi ij star minus phi ij at nth level. So all phi ij minus 1, ij plus 1, I plus 1j, I minus 1j, all these phi values are at nth level. From there we are calculating phi ij star, and using phi ij star and nth level value, and having performed the over relaxation exercise, we are calculating phi ij at n plus 1th level, at the next iteration level. So this way we can keep on iterating till we get a constant value, or the values of ij are ij remain unchanged at every cell or every point. Then we have gotten the final solution. So that is what is the solution strategy of basically Laplacian phi del 2 phi del x2 plus del 2 phi del y2 equal to 0. While doing this, we have learned how to handle the second order derivatives, number one. And number two is we can see, instead of x equal to constant line, y is equal to constant lines, which make basically Cartesian grid. Instead of that, we used curvilinear grids, basically body conforming zeta equal to constant, eta equal to constant lines, and we got this expression. But this expression, or expression 32, whatever we consider, they are same. We get this 32 or 33. But now if you change the grid to basically Cartesian grid, as I said, that all x equal to constant line, y equal to constant lines, Cartesian grid, then this expression you can test it in your notebook. This expression will be transformed into equation 35, which is phi I minus 1j minus twice phi ij plus phi I plus 1j divided by delta x square plus phi j minus 1 minus twice phi ij plus phi I j plus 1. So, and divided by delta y square. And so this is basically central difference in x direction, central difference in y direction. So this is finite difference quotient for del 2 phi del x2. This is finite difference quotient for del 2 phi del y2. And we get this through difference approximation. But finite volume method is basically integral representation. But finally, we can see that they are equivalent if the curvilinear grid is confirmed, is curvilinear grid is changed to Cartesian grid. So this is possible for cylindrical polar coordinate and spherical polar coordinate also. The similar exercise can be done. So what we did in this part of learning finite volume method, we have just conceptualized the ideas and then implemented it on simple equations, but directly or indirectly, our target was to basically integrate the variable, its first order derivative, its second order derivative in the elemental control volume, elemental control volumes, to get the final set of algebraic equations. So with this, we will stop today, and in the next class, hopefully, we'll take up another new topic. Thank you very much. Thank you.